In this video, we will look at electric charge. Electric charge is a property of matter. That means every piece of matter can be assigned a charge, which could be positive, negative, or zero. Since electric charge can be described by just a single number with units, it is a scalar. The SI unit for charge is the coulomb, which is denoted by the capital letter C. In this course, we will usually measure electric charge in coulombs and occasionally in multiples of E. E is the amount of charge on a proton. One of the properties of charge is that it is quantized. Saying that it is quantized in units of E means that charge always occurs in multiples of E. So you can have a total charge which is, say, minus 3E, or plus 50E, or 0, or minus 49E, but you cannot have a charge which is minus 7.5E. You cannot have any fractions of E. So charge always occurs in multiples of E. Could be positive, could be negative, could be 0, but multiples of E. Electric charge is conserved. This means that if you have a closed system, the amount of charge in that system, the total amount of charge, always stays the same. This also means that if you bring some positive charge into being, then you must also bring an equal amount of negative charge into being. You cannot create charge from nothing. The total charge must always stay the same. And finally, a bit of notation. Electric charge is usually denoted by the variable Q. Capital Q, small q, doesn't really matter. So we've mentioned the unit E, and how is that related to the coulomb? So 1E is 1.602 times 10 to the negative 19 coulombs. So we can see that the coulomb is actually a very large unit of charge. The charge on one proton is plus 1E, the charge on an electron is minus 1E, and the charge on a neutron is 0. These three particles, the proton, the electron, and the neutron, make up atoms, and atoms make up all the everyday matter that we see around us. To get a better idea of how big a coulomb is, we can look at the following comparisons. Well, we've already seen a proton is roughly 10 to the negative 19 coulombs. When you suffer static shock, a static discharge, the amount of charge transferred in that little spark is about 10 to the negative 9 coulombs. A lightning bolt will transfer anywhere from 5 to 300 coulombs. 5 is typically what an average lightning bolt transfers, 300 for some of the larger ones. And a AAA battery rated at 1200 milliampere hours, in the course of running down until it's completely discharged, will pass 4,320 coulombs. Of course, coulomb being an SI unit, we can apply all the usual prefixes. So we can talk about millicoulombs, microcoulombs, megacoulombs, and so forth. Here's an example. A metal ball with charge negative 3 coulombs is charged to a metal ball with charge plus 7 coulombs. What is the total charge on the two balls now? Take a moment and try and figure this out by yourself. We will now discuss the answer. Since charge is conserved, we know that the total initial charge, must be equal to the total final charge. The total final charge is the charge on the first ball plus the charge on the second ball. And -3 plus 7 gives us 4 coulombs. How are these 4 coulombs spread? We don't quite know. If the balls are of the same material and of equal sizes, then they'll probably be split equally. But if they're of different sizes, they need not be split equally. But since we were asked for just the total charge of the two balls, we can answer 4 coulombs. Here's another example. A metal ball with charge -5 coulombs is manipulated by other objects until it has a final charge of -6 coulombs. Were electrons added or removed? And how many electrons were added or removed? Again, pause the video here and try and solve this by yourself. Alright, on the next slide we will proceed to the answer. Since the ball became more negative, going from -5 coulombs to -6 coulombs, and since electrons carry a negative charge, electrons were added to the ball. To find the number of electrons transferred, we look at the total charge transferred divided by the charge per electron. Since the change in charge was -1 coulombs, we have -1 coulombs divided by the charge per electron, which is -1.602 times 10 to the -19 coulombs per electron. This gives us 6.24 times 10 to the 18 electrons. We will now discuss the structure of matter a little. An atom consists of a positively charged nucleus surrounded by a cloud of negatively charged electrons. The nucleus contains both protons, which are positively charged, and neutrons, which are neutral. Since the protons are positively charged, two protons in the nucleus will repel each other. The protons and the neutrons are held together by the strong nuclear force. Since the electrons are negatively charged, they are attracted to the positively charged nucleus by the electrostatic force of attraction. This is what keeps the electrons around the nucleus. For a neutral atom, the number of electrons is equal to the number of protons in the nucleus. As a whole, thus, the atom is neutral. The same element can have different isotopes. These isotopes differ in the number of neutrons that there are in the nucleus. For example, carbon occurs in both carbon-12 as well as the carbon-14 isotope. The carbon-12 isotope has 6 protons and 6 neutrons and 6 electrons. The carbon-14 isotope has 6 protons and 6 electrons, but 8 neutrons. The nucleus is extremely tiny. While the typical size of the atom is an angstrom, which is 10 to the -10 meters, the typical size of the nucleus is a femtometer, which is 10 to the -15 meters. So you can see that a nucleus is somewhere between 10,000 to 100,000 times smaller than the atom. However, even though the nucleus is tiny, it is massive. Most of the mass of an atom is contained in the nucleus. This is because the protons and neutrons each are roughly 1800 times more massive than the electron. And since the number of protons is equal to the number of electrons for a neutral atom, the nucleus will always be at least 2000 or so times more massive than the rest of the atom. You sometimes hear that atoms are mostly empty space. This is incorrect. Atoms are mostly electron clouds. The nucleus, which contains most of the mass, takes up only a very small portion, that is true, but the great part of the volume of the atom consists of the electron cloud. How can we charge an object? The different ways of charging an object are the transfer of charge, that's in particular by using friction, creating equal and opposite amounts of charge, charging by conduction, and charging by induction. Both charging by conduction and charging by induction are actually related to the transfer of charge, and we will discuss these after we have learned a bit more about conductors and insulators. For now, let us look at the transfer of charge, that is charging by friction. If you rub plastic rods with fur, the fur becomes positively charged and the plastic rods become negatively charged. If you rub glass rods with silk, the silk becomes negatively charged and the glass rods become positively charged. This was in fact actually how they first decided the conventions of positive and negative. They knew that the type of charge on the plastic rod was opposite to the type of charge on the glass rod, and then they arbitrarily decided that the one on the glass rod should be called positive and the one on the plastic rods, or they were using ebony rods probably at the time, should be called negative. And this convention persisted. And this convention was in fact set up by Benjamin Franklin. So, how did the glass rods get positively charged? What happened was that when you rubbed the glass rods with silk, the glass rods lost electrons, and those electrons were transferred to the silk. The deficiency of electrons in the glass gave it a net positive charge, as there were more protons in the nuclei than there were electrons around them. And the excess of electrons on the silk gave it a net negative charge. So this is an example of charging by friction and transfer of electrons. We can also create charge essentially out of nothing. Doesn't that violate charge conservation? No, because the total amount of charge still stays zero, but we get equal amounts of positive and negative charge. What happens here is a gamma ray, which is a type of photon, collides with the nucleus, and then the gamma ray is converted into a positron and an electron. This is an example of Einstein's famous relationship E equals mc squared. Here we have energy in the form of a gamma ray being converted into mass, an electron and a positron. What role does the nucleus play then? It's important to understand the electron and the positron do not come from the nucleus. They were created from the gamma ray. However, a gamma ray cannot by itself spontaneously turn into a positron and electron, because that would violate either energy conservation or momentum conservation. In order for both energy conservation and momentum conservation to be upheld, what happens is the gamma ray collides with the nucleus and transfers a little bit of momentum and a little bit of energy, and the remaining energy and momentum are converted into the positron and the electron. This process is called pair production. We can see that before the collision, the gamma ray had a net charge of 0, And after the collision, the gamma ray is gone, and we have a pair of a positron and electron. And again, the net charge is 0. So charge is conserved, but we have also created two charged particles. Of course, we can also look at the opposite process, where an electron collides with a positron. Since the positron is the antiparticle of the electron, the two annihilate each other, and their mass is converted into energy, and we get a pair of gamma ray photons. We can see that energy is conserved, or rather mass energy is conserved. The mass of the electron and the positron and their kinetic energy are converted into the energy of the two photons, and we can also see that momentum is conserved. Here the electron and the positron have opposite amounts of momenta, so the total momentum before the collision is 0, and here we see the two photons are heading in opposite directions, and so again the total final momentum is 0. So energy is conserved and momentum is conserved, and charge is conserved. The total net charge before was 0, the total net charge afterward was 0. This process is called pair annihilation, since the electron annihilates the positron. Finally, let's briefly mention how charges interact with other charges. It's a simple rule: like charges repel and opposite charges attract. The force between two charges, between 2 point charges, is given by Coulomb's law, and that will be discussed in another mini lecture. One final point. When you press your hand against a wall, what stops your hand from going through the wall? From Physics 110, we know that the wall exerts a normal force on your hand. But what is the nature of this normal force? What actually is happening is that the atoms in your hand are coming into contact with the atoms in the wall. Both the atoms in your hand and the atoms in the wall have electron clouds, and these electron clouds are negatively charged. Since like charges repel, the electron clouds of the atoms in the wall repel the electron clouds of the atoms in your hand. And this we perceive as a normal force. So, electromagnetic forces underlie most of the forces that we see in everyday life. Normal forces, elastic forces in a rubber band or spring, frictional forces. Most of the forces we see, except for gravity, are caused by the interactions of atoms with each other, and these interactions take place through the electromagnetic force. That's all for this lecture. I'll see you in the next.